Hey guys, this is Kerry, and in this lesson we're going to be talking about simplifying square roots. So triangle ABC is a right triangle, so make sure that you draw the picture. Now you can tell it's a right triangle because this angle here is 90 degrees, so we'll mark that with a little box. If angle C is the right angle, so that means angle C goes here, and then the other letters that we're going to be using are A and B, and they didn't give us any information about these, so we can put A here and B here. Alright, let's label our side lengths. AB is 13, BC is 12, and we need to find the length of side AC. So when we need to find something and it's unknown to us, we oftentimes use the letter x. So now we need to set up an equation in order to solve for x. And that equation is going to be something very familiar to you called the Pythagorean theorem. So take a second and try to write down what the Pythagorean theorem is. Hopefully you get a squared plus b squared equals c squared. Now when you plug in these numbers, the most important thing to remember is that c is always going to be the hypotenuse, the longest side. This is also always the side that's across from the right angle. So we plug in c is 13, and here for a and b, we plug in these sides, and it doesn't matter the order that we plug them in. So we can do x squared plus 12 squared equals 13 squared. Now, when we have a number squared here, like 12 squared, that means 12 times 12. So you can either do that in your head, or you can bring up your calculator and do it on your calculator. That gives us 144. 13 squared, you can put in your calculator by doing this, and that gives you 169. All right, so to solve for x squared, we need to do inverse operations. Minus 144 on both sides. That gives us x squared is equal to 25. Now the final step to solve for x here is to get rid of the square. And what's the opposite of squaring? Well, the opposite of squaring is square rooting. So we use the square root, and that cancels the square. But if we do square root to this side, we have to do square root to this side. So now x is equal to, and if you want to type this in on Desmos or on your calculator, you can type in like this. And it should auto-change the word square root here to the symbol square root. But this one we can actually do in our head because this is a nice square root. What the square root asks is, what number times itself equals 25? And that's the number 5. So the square root of 25 is 5. All right, so there are many of these nice square roots out there. Some other nice square roots are the square root of, 36. Because what number times itself gives you 36? That's 6. The square root of 49, what number times itself gives us 49? Oop, I don't want to write that all there. Just kind of the thought process, what number times itself gives us 49? It's going to be 7. And finally, one more example would be the square root of 100. What number times itself gives us 100? That's going to be 10. And so numbers like this have a name. These are called perfect squares because they work out really well. But it turns out that this is not the norm. It turns out that actually most square roots turn out to be really gross decimals. So if we were to pick like just a random number here, square root of, let's just choose like a low number like 8. It turns out to be like this terrible decimal. Square root of, square root of 9 works out fine because that's a perfect square. 3 times 3 is 9. But if we change it to 10, just this terrible decimal. So it turns out that the mathematician that discovered this was named Hippasus, and he lived in Greece. So it's kind of a cool story in math. Hippasus was actually a member of a mathematical cult. And that mathematical cult was actually called the Pythagoreans. And these guys were a bunch of ancient Greeks, and they worshipped numbers. They thought that numbers were like the meaning of life and stuff. And so they thought, because numbers were like the meaning of life, numbers were the most important thing in the world, that numbers should be nice and friendly. So the Pythagoreans were super cool with like the square root of 100 being 10. That was like, hey, this is so neat. Like the world works exactly as it should. Everything is perfect. But Hippasus actually was the one who discovered that there are ugly square roots, like the square root of 8, or what do we get for the square root of 8? Let me go back to Desmos. So somehow without a calculator, Hippasus did this. 2.828 This is a terrible decimal here. 427 ... And it turned out, actually, that this never repeats, and it goes on forever. So Hippasus was like super pumped about his new discovery. He's like, oh my God, I can't wait to tell all the other Pythagoreans about these crazy decimals that go on forever and never repeat. So he did. He told the rest of his math cult about this, and it kind of contradicted the idea that math was actually perfect. And so what the Pythagoreans did was they actually killed Hippasus because he discovered this. They took him out on a boat, and they beat Hippasus to death for discovering that there were decimals that went on forever without repeating, because it contradicted this idea that numbers were these perfect things in the universe. So square roots, our topic for this lesson, come up from the Pythagorean theorem, but in particular, they can be a dangerous thing to work with, and we'll see that a couple of times in this unit. So what we're going to talk about today is these decimals are not a very nice way of writing these. And when you have a perfect square like this, it's very easy to rewrite. You just find that nice number. But what happens if you have situations like these that are not so nice? How do we find these square roots? Well, to do that, we're going to use a nice method that might be familiar to you. So here we got the square root of this fraction, and that looks terrible. But this one's actually not too bad. The square root of the fraction, you just take the square root of the top and the square root of the bottom separately. And square root of 16, oh, that's one of our perfect squares. What number times itself is 16? Well, it's 4 times 4, so we get 4. And this one is 2. What number times itself is 81? It's 9. And we're done. Much nicer than writing it as a decimal. This decimal wasn't too bad, though. Actually, if you put it on your calculator, I think you get like 0.44444, which is like kind of not so bad. But Hippasus would recommend to us not to write as a decimal based on his experience with writing things as decimals. So this is called simplifying a radical. So we're going to be simplifying each one of these. So let's check out square root of 72. Now this one is not as nice. Square root of 72 we run into a big problem with. For square root of 72, we can't actually do it. So we need a new method. And that method's going to be called the jailbreak method. So for the jailbreak method, what we're going to do is we're going to break 72 down into all of its factors. So you can create a little factor tree, and we're trying to think, well, what numbers multiply to make 72? What numbers divide 72 nicely? And your answers might be different than mine, but I see that it's even. So for me, that's immediately 2. Then I pop over to my calculator. I'm going to see 72 divided by 2. Okay, well, that's 36. So 2 times 36, yeah, that is 72. And there's a variety of ways to do this, but I like to keep breaking these down. So for 36, that's going to be 6 times 6. 2, 3, 2, 3. All right, so putting things together here, it looks like we've got, putting all the 2's together, 2 times 2 times 2, and then the 3's here, 3 times 3. Now this multiplication problem, 2 times 2 is 4, times 2 is 8, times 3 is 24, times 3 is 72. So same thing as what we had before. But the benefit of having all the factors like this is that we can use the jailbreak method. So you can see the square root as a jail, and getting out of jail is difficult, so you need to have a twin to get out of jail. So what we're going to do is we're going to look for twins here. Now 2 has a triplet, but that's more than twins, so we just want twins. Yeah, there are twins right here. So these 2 twins are going to try to break out from the square root jail, but breaking out of jail is difficult. So one of the twins will die, and the other one gets out alive. Now, do we have any other twins? Yes, we have these 3's. So these 3's are going to try to break out of jail as twins as well, and just like happened to the 2's, one of them is going to get out, the other one is going to die because getting out of jail is difficult. So then left inside of the square root jail is just the single 2 right here, because this 2 got out and this 3 did, and that will leave us with 6 square root of 2. Much better than our infinite non-repeating decimal that got Hippasus killed. Our jailbreak method gives us a nice answer here. And if you want to type this into Desmos, you can type 6 square root 2, and it will automatically transform this sign into the square root sign. All right, so for this one, the next one here, we're going to need to use our jailbreak method. 9 square root of 40. All right, well 9 is outside, and then we need to break 40 down. Perhaps you think 8 and 5. I know I do. This will give us 2 and 4. This will give us 2 and 2. So we're left with 2 times 2 times 2 times 5. 2 times 2 here. Well, getting out of jail is difficult, so we're going to look for twins. We've got triplets, again, but we don't want triplets. We only want the twins here, so we're going to circle those. When they try to escape, one gets out, the other dies. That always is the case here, and we get 18 square root of 10. Because the 2 that gets out needs to multiply with the 9, because the operation here, if we don't write a symbol, is multiplication. So 2 times 9, and that gives us this. And that's the furthest that you can break down. Now, where did the 10 come from, you might be wondering? Well, who was left in jail? 2 times 5, and that's why it's 10. All right, for number 5, your instinct might be to go with the jailbreak method. But it turns out that's overkill on this one, because the square root of 16, if we're observant here, that's one of our perfect squares. That's just 4. And a lot of students will accidentally write square root of 4, but you've actually done the square root to 16 and gotten 4. And then between 5 and square root of 16, we don't have an operation, so we're going to put multiplication there. Because whenever we don't have an operation like in 5x, it always stands for multiplication. All right, so we have 5 times 4. This is just going to be 20. All right, square root of negative 4. Here we run into an interesting challenge. The square root, remember, what number times itself gives us negative 4. So we're looking for a number, same number here, that's going to give us negative 4. Well, maybe we try negative 2. Well, negative 2 times negative 2, oh, well, that doesn't work. That's going to give us negative times negative. That gives us positive 4, which isn't the same thing as negative 4. All right, so maybe next idea, negative 2 times 2 would give us negative 4. But remember, it's times itself, so these two numbers have to be the same number. So that doesn't work, even though it gives us negative 4. All right, well, 2 times 2 maybe. And that's just positive 4 again, not negative 4. So this actually turns out to be impossible. We can never take the square root of a negative number because there's not going to be a number that times itself gives us a negative. Because we need to have, to multiply to make a negative, we need to have a positive times a negative. And that can never be the case if it's going to be the same number. This one, though, is actually possible. The square root of 4, that's just 2. So the negative sign stays. Square root of 4 is 2. Make sure you don't put that square root, though, because you did the square root to 4. So it's no longer there. You've done it. All right, now the rest of today's lesson is practice. If you're not sure how to do problem number 1, I'm going to highly recommend taking a look at the jailbreak method from these. Remember, you're looking for twins. And then as you continue on, I think you'll find some interesting problems that get some more difficult ideas. All right, good luck with today's lesson, guys.